Okay, so continue our discussion of the gross spaghetti equations. We have these various physical quantities, including, here they are, the energy density, the vorticity, and as preparation for analyzing the dynamics of vortices, we're proving theorems. We're looking at theorems that discuss the relationship between these two quantities. So this will be key in study of vortice dynamics. Okay, and so, and these have conservation laws. Okay, and so the theorem I'm aiming for is this one I've shown you several times, which says that if the vorticity is moderately concentrated, in this sense, and if the energy is under control, then in fact the vorticity is highly concentrated. That's what the theorem says. Okay, and so we proved a couple of lemmas. The first tells us what we have to do to prove the theorem. So it says, suppose I want to prove an estimate of this sort. I want to control the flat norm distance of the vorticity of a function of psi to a bunch of delta functions. So I'd like the right-hand side to be small. It says what I have to do is I have to, well, if I know the energy is not too big, so for me, the energy will always be order log 1 over epsilon. So big, but not very big. Divergent as epsilon goes to 0, but divergent very slowly. Okay, and so what this says is if I can contain the set where the function psi has modulus less than half, if I can contain that in a unit of balls, and if the sum of the radii of the balls is small, then I get the kind of estimate I want. So that's the lemma. Let me make a remark, which I didn't say before. So, and so a little technical issue arises here. So I have these balls, small balls, and some of them may intersect the boundary if I'm unlucky. And I messed around. I said, well, okay, in that case, if the ball looks like this and the center's out here, I can't take this. Normally, I would take this C sub K to be the center of the kth ball. In this case, I can't do that because the center's outside, whatever. Okay, so the remark I would like to make is that if any of the balls happen to touch the boundary, well, what can I do? I can take C sub K to be, well, okay, so in general, we can take C sub K to be any point in the ball and in the domain. Like, and so for example, in this case, I could take C sub K to be here, a point on where the ball intersects the boundary. If I do that, then what happens, I'm only considering test functions who vanish on the boundary. And so if I do that, then when I when I multiply by such a test function and integrate, I will get the test function phi evaluated at this boundary point, which is 0. And so in fact, I can omit from this sum every ball who touches the boundary with no change to the estimate. We can set dk equal 0 if the ball intersects the boundary of D. Okay, that's a remark. Okay, so we proved that lemma. And the other lemma we proved says the following. It says that if I have a ball who is, so the reason I like, I don't want to worry about things who touch the boundary, partly because of this hypothesis. So in the second lemma, I assume that my ball is completely contained in the domain, in the open set. I've written this a bit differently from how I did last time. But last time I said that D was the absolute value, and I wrote D down here. Here I've said that D is the number, the integer, who can be positive or negative, and I've written the absolute value of D down there. Okay, so anyway, so if I have a ball with okay, I guess for this I need psi greater than 0 on the boundary of the ball, so that this D is well defined. Then we have a lower bound for the energy integrated around the boundary of the ball. And basically the lower bound is like d times log 1 over, or say d pi times log 1 over r. Okay, so the lower bound is, this would give me pi d over r for a ball radius r. And lower terms, I don't worry about, because I'm eventually going to integrate this lower bound over r, and the lower terms will integrate to a finite number, whereas the leading terms will be divergent as epsilon goes to 0. Okay, so this is what we've done so far. And let me then proceed. So the first thing I want to do is the following. I'm going to, and so again, my goal is to, as I said, to cover the 0 set, or the set where the set S stands for small. S is the set where the function is small, to cover that set by balls. Okay, and so let me first introduce this. We'll say, so here, okay, it'd be better if this were on the same page, but so capital lambda epsilon is going to be the capital lambda epsilon of S will be the integral from 0 to S of little lambda epsilon of R, dr. Okay, and so the main point to look here, let me draw a picture of lambda epsilon. It looks like basically, 1 over epsilon, and then it behaves like a, pi over r, pi over s. Okay, so it's a bounded non-increasing function. Okay, and so this capital lambda epsilon is just the integral from 0 to out to s of little lambda epsilon. And it has some properties we can easily see. So first of all, this is true. The first one is true for any decreasing with any non-increasing function. So if I integrate from 0 out to r, or to r plus s, the integral from here out to there will be smaller than the integral from here to r, and the integral from here to s. Sort of obvious, due to the decreasing nature of the function. Okay, next. If I look at the map that takes sigma to 1 over sigma, this integral, and so what is this? This is if I look at this thing, 1 over sigma lambda of sigma, that's just the average of this lambda epsilon. And clearly, if I have a decreasing function, if I average over a longer interval, I get a smaller number. Okay, so this is non-increasing, and it's also bounded by the alpha normal over C epsilon. Okay, and then it's easy to verify that this lambda epsilon is always bigger than pi log r epsilon minus constant C. That's because the integral of, well, if I integrate this thing, if I integrate here, I'll get a constant. I'll get C pi over epsilon, C pi epsilon over 2 times 1 over C epsilon. So I'll get a 1/2, I guess. And then if I integrate from this number out to infinity, the error term here will integrate to a finite number. So, okay. So, and so the main contribution is the integral from order epsilon out to r of 1 over s ds times pi, and that gives me pi log 1 over epsilon, log r over epsilon. Okay, and then finally the important one, which is that this function capital lambda provides a way of keeping track of lower bounds, of lower energy bounds on annuli. And so here's what this says. Let's so the so I'm in so my situation is I'm always in some set D, and I have this function. Oh, okay. Oops. I activated Siri by mistake. Siri is listening to this lecture and reporting back to Cupertino on everything I say.
The definition of the word activated is sewage treated with erosion and bacteria to aid decomposition. The word activated has 3 other definitions.
Sorry. Okay, it's gone away. So sorry about that. Okay, so I wrote H1. So I guess it's easier if we assume things are C1. For like the definition of degree involves the integral of the gradient around a boundary. In fact, all this stuff is true for H1 by density arguments. But let's ignore that. Okay, so I have this function in C1, say, and I assume I have a point A and a ball of radius little r and a ball of radius capital R around A, and I assume that psi is bigger than a half in this annulus. And I assume that the degree, say on the inner ball, the winding number of the phase is this number d, some number which is non-zero. Okay, then in fact, the winding number can't change in this annulus where the function is bounded away, where the modulus is bounded away from zero. And so the winding number on every, if it's under these hypotheses, the winding number on every radius between little r and capital R will be the same number d. The degree will always be the same number. Okay, and so then from the previous lemma, we get well, it's the integral over from little r to capital R of the integral over the ball of radius s. Sorry, the sphere of radius s. That's right, Hausdorff measure, surface area, or arc length, if you like. Okay, and the previous lemma tells us exactly that this is bigger than lambda epsilon of s over d ds. I'll make a change of variables. Let's say, let's write this as s over d, and I'll get a factor of d. Let's call s over d sigma. And so this is just the integral from 0 to capital R minus the integral from 0 to little r, which is exactly d times, sorry, and when I make the change of variables, I have to change the limits of integration as well. D times lambda epsilon of r over d minus lambda epsilon of little r over d. Okay, and so just by integrating the previous estimate, we get this one, which is exactly the one up here. Okay, and so using this, my plan is to prove the theorem. Okay, now I'm going to start. I have to, in the interest of time, I have to start lying, and so that's what I'm going to do. Here it is. So to convey the spirit of the argument, I'm going to sweep certain technical details under the carpet. And so here's this quote unquote lemma, which is not correct as stated. And later on, maybe I can tell you what goes into the proof and what's not correct and how you would fix it. But for now, I want to just assume it's true and use it to prove something, to give it interesting and attractive argument that is actually rather powerful. Okay, and so here's the, so my strategy is, again, my goal is to cover the set where psi is small. So I'm imagining psi is some h1 function, and I want to think it's being maybe a solution of the Gross-Petit's equation or initial data or something like that. I have some information about the energy and the vorticity, and I'd like to use that information or relate that information in some way of covering the set where the function is small by balls who have small radii and on which I can control the energy and the winding number, because the winding number is really going to translate information with the vorticity. Okay, and so let me imagine, and so the way I'll do this is I'll start by covering my small balls, and I'll let the balls grow in a certain way. There's an algorithm for doing that. And so I'm going to just assert that there's a way of getting started. So I start with a function psi, and I claim that there exists, I assert without proof, and it's not even correct. I assert that there, but it's almost correct. I assert that I can, and I'll always draw the same picture. I have this function, this set d, and this function psi, And I assert that I can just find a bunch of closed balls who cover the whole set where, so there, there may be some there's some set in here someplace where the function drops below half in modulus. And the claim is I can cover that by balls, closed balls, pairwise disjoint, didn't say that, pairwise disjoint. And not too small, because in my previous lemma up here, I needed, and here I should have said if little r is bigger than epsilon, since in the previous lemma, I needed to assume that little r was bigger than epsilon. So I don't like balls that are too small. Okay, so then the assertion here, the incorrect lemma is that I can cover the set where the function is small by balls who are not too small. Okay, it's good. Okay, all of them intersect the set where it's small. I don't know how I can use that. And here's the crucial thing: I have a lower energy bound on each of these balls. So on each ball, on its intersection with the domain D, I have at least the energy is proportional to 1 over epsilon times the radius. So typically one should imagine these being balls with radius of order epsilon, and the energy will be of order 1 in each ball. And note that for any value of sigma, this, I think I said this before. Oh, I forgot to say this, but this quantity, 1 over sigma times lambda epsilon sigma, is always at most 1 over constant times epsilon, indicated in the picture. Okay, and so then this number r naught over c epsilon is always bigger than r naught over sigma times lambda epsilon sigma for any sigma. Okay, and so so the second inequality here is easy property of this function capital lambda, and the first inequality is the part where I'm being a little bit dishonest. The idea is if the degree is non-zero, well then it's pretty easy to show that the energy must be order 1, and if the ball is big, well then on all radii bigger than epsilon, we can apply the previous estimate to find quite a lot of energy. And so one uses these kinds of considerations. But let's pretend the lemma is correct and see what one can do with it, as I've written here. So so this is going to be the main tool in the theorem, in the proof of the theorem I stated earlier. So let me say, any questions? How unhappy are you with what I've just done? I've said, here's a lemma, it's not even true, I'm not going to prove it. I'm asking you to accept it. So I'll be happy to talk about it later on in more details. But again, well, no, I've said, I was just going to repeat myself, so let's not do that. Okay, so hopefully, this doesn't make you too frustrated. Okay, so then here's what I want to do. I'm going to prove the following proposition. So I assume I have, okay, a C1 function complex valued on my domain D. And I have this collection of balls who I've found above who cover the set where the function is small, and such that for each ball, the energy of that ball is proportional to 1 over epsilon times the radius. So there can't be, there can't be too many of these balls, because the total energy, well, if I'm always imagining the total energy is of order log epsilon, well then each ball has energy at least order 1, and so the number of balls can diverge, but it can converge slowly. Okay, so I found these balls. There's a, at most log 1 over epsilon balls. For each one of them, there's a degree, because, I'll draw my picture again, my beloved picture. So here the function is small, and then there are these balls covering it. So because the balls cover the set where the function is less than or equal to half, on the boundary of the balls, the function is certainly greater than or equal to half, and therefore the degree is well defined. And so we assign a degree to each such ball. Let's call that D0K. And let's say that sigma naught is the minimum of the radius of the kth ball divided by the degree of the kth ball. And we'll set that plus infinity if the degree is 0. And so then so each ball has a radius as a degree. So if all of the balls have degree 0, then sigma naught is plus infinity, but nothing very interesting is happening. That says essentially there's no vorticity, because vorticity, we should think of vorticity as being degree or winding number. Okay, and so in the interesting cases where there's some vorticity, some of the balls will have non-zero degree, and the sigma naught will be finite. Right. And as soon as sigma naught is finite, if I imagine the energy is of order log epsilon, well then, if I look up here, each of these R sub k's will be at most epsilon log epsilon. Those are small numbers. And so again, sigma naught will be like most epsilon log epsilon. It won't be too big. Okay, so we should think of sigma naught as being epsilon log 1 over epsilon under our hypotheses. Okay, and so then for every larger value of sigma, for every sigma bigger than sigma naught, I can find a collection of balls that, okay, they continue to cover the set where psi is small. And what happens as I increase sigma, basically I'm increasing the radii of the balls. So so by definition, for sigma naught, it's true that sigma naught is less than or equal to R sub k over D sub k for every k. So sigma naught is so sigma naught times D sub k is less than or equal to R naught. This is true for sigma naught by the definition of sigma naught. And then we want it to continue to be true as we increase this parameter sigma. Here's the crucial property again. And so I'm interested in the lower energy bounds. This is the crucial property. And so this says that as I increase this parameter sigma, I always have a lower energy bound on all the balls. And then, okay, down here, this is less important and interesting. The sum of the radii is a continuous non-decreasing function. Okay, let's see what this says, this one. And so let's see. Also note that if, sorry, I want to do this here. So if I have equality here, then what happens, R sub k over sigma is D sub k. And we have lambda of R. Okay, and so this is like pi times d times log of the radius over the degree minus a constant, because that's what this capital lambda is like. Radius of degree times epsilon. Okay, and so that's that's not a bad lower bound. In particular, if D is equal to 1, this is sort of the right lower bound. We saw that we expect on a ball of radius R to have so we saw that if I make this equivariant assumption, if I assume that I have something of the form R f of R e to the I theta, and I compute the energy on a ball of radius R, it'll be like pi times log of R of epsilon minus up to a constant. And so this says that we have, so we'll find all these balls on which we have the same energy scaling, no matter what the original distribution of the set S is where the function psi is small. That's the nice thing about this estimate. Okay, and so that's the wrong thing. Let's see if we can sketch the proof of this. Okay, and so I'd like to prove this. And so what I'll do is so proof of the proposition. Are there any questions or anything? Okay, let's see if we can do it like this. So I have, as usual, this set where psi is small. And I covered, and I've assumed, or I've stated that we can somehow cover this in balls of size at least epsilon, on which, so for every ball I have the integral over the ball of the energy is greater than the radius over the degree, no, radius over sigma times lambda of sigma, and sigma is the min of the okay, so we always have this. We have this when the process starts. So here's what I want to do. I'd like to. So they're closed balls. They're pairwise disjoint. I should have said that. Sorry, I forgot to say that. Closed pairwise disjoint, and so they're bounded away from each other by a certain distance. Let me get rid of some of them. It's too crowded. Okay, and so what do I do? I'll define. And so I should have said this is the minimum over, and let me say, if they're balls who touch the boundary, I'm not going to worry about this. So it's the, so we'll say, right. So sigma is the, I look at this ratio of radius to degree for balls who are entirely contained in this, in the domain. Balls who touch the boundary, just don't worry about it. Okay, and so then I have this number. What I'll do is so for some of the balls, I'll say a ball is minimizing. A ball is minimizing if RK over DK is equal to sigma. So these definitions, I'll make them for initially for sigma naught, but then I can do the same thing for any value of sigma. And so there may be some, and so if that's not true, if RK over sigma k is bigger than sigma, well then my lower bound is sort of, I have extra energy in the lower bound, and so I have a ball that's too big. That's okay. Okay, so what I want to do is I'll consider all of them, and so let's assume that these balls are, well, okay, let's assume for a country, for that they're, let's assume that these are minimizing here, here, and there. So I look at the minimizing balls, and what I want to do is I want to expand, I want to grow them. So I want to increase sigma, and increasing sigma is the ratio of the radius to the degree. Outside here, outside the purple balls, the modulus is bigger than a half. And so if I look at any ball around here, the degree is always going to be the same, at least until I intersect some other ball. And so if I imagine growing these balls, if I imagine increasing sigma, I change the radius, I don't change the degree. And so increasing sigma just means letting the radius grow. And it means letting the radius grow at a rate which is proportional to the degree of the ball. And so a bigger ball will grow faster if I want to keep sigma constant. Okay, and so what do? I increase sigma, letting all minimizing balls grow while holding sigma constant, or as sigma increases. Okay, and so then maybe, and so these will grow. At a certain point, they may hit each other, or they may hit the boundary. Okay, if they hit the boundary, I stop. So I stop if any ball hits the boundary or hits another ball. If two or more balls hit each other. Okay, and then I want to, okay, as sigma increases, the collection of minimizing balls so a ball who's a priori non-minimizing may become minimizing as sigma increases. And so suppose this R over D is equal to epsilon a priori, and there's some ball for which the ratio R over D is 2 epsilon. Well, when I increase sigma to 2 epsilon, that ball will suddenly become minimizing, and then at that point I start to let it grow. Okay, so this is the algorithm. And I want to argue that as I do this, okay, so I've said, I've described this growing ball. I want to argue that as I do this, all of these properties are preserved. Okay, certainly it'll still be true that I'm just growing things, and so they'll always contain the set S. This is true by fiat. I always increase the balls in a way so that Rk over dk is equal to sigma for the minimizing balls, and by definition is greater than sigma for the non-minimizing balls. Okay, this we can see, it's easy to see. And so this is the hard part, or the non-obvious part. Let's do that. And so the energy lower bound. So we have to look at the, what do I have here? Well, let's say Rk of sigma, the energy so this is the energy of, so I imagine I'm say increasing from sigma naught to some larger value of sigma. Okay, and this would be true also if I increase from sigma 1 to a sigma 2. It's the same argument at every step. So let's do this sigma 1 or sigma 2, sigma 2, sigma 1, sigma 1. Okay, so by induction, if you like, this is bigger than, what did I say? Rk of sigma 1 over sigma 1 times lambda of sigma 1. And here, by the previous lemma, this is, so this is the where this capital lambda appears. This is bigger than dk times lambda epsilon of rk over rk of sigma 2 over sigma 2 minus lambda epsilon rk of sigma 1 over sigma 1. And because the ball is minimizing, by definition of minimizing, this is exactly equal to rk of sigma 2 over sigma 2. That's what it means for a ball to be minimizing. And then this and this cancel because the degree doesn't change. And so I get dk of, I get what I wanted. Rk of sigma 2 over sigma 2 lambda epsilon of sigma 2. Okay, and so if I grow the balls in this fashion, this is my estimate, my lower estimate by something of this form is preserved during the growing process. And so this is just a convenient way of packaging the earlier lemma here, which really just follow from this sort of easy calculus considerations on a single radius. We did these easy calculus arguments on a single radius. By iterating those, we got this estimate, and then so we're just packaging that in a nice way. And okay, so we found that I can grow balls, and my estimate is preserved. If now consider a non-minimizing ball. And I want to show again that this inequality is true. And so for a non-minimizing ball, well, as I change sigma, the ball doesn't change. And so what happens for a non-minimizing ball, let's say again, I'm increasing sigma from some sigma 1 to sigma 2. If I look at this inequality, the left-hand side isn't changing because it's just the same ball. I'm not doing anything. On the right-hand side, as I increase sigma, remember we said that 1 over sigma lambda from sigma is a decreasing function of sigma. So I'm just getting a worse estimate, but it's always true. So as I increase sigma, I'm getting a worse estimate of non-minimizing balls, but always satisfied. It's true. And so, okay. And so step 1 in the algorithm is I start with these balls. I grow them as described, and I can see that as I grow them in this fashion, each ball will continue to satisfy this estimate, and the other ones are easy. Okay, what happens? Well, if one of them hits the boundary, I just forget about it because I've only I only ask for when I consider minimizing balls, I only look for things who don't touch the boundary. I only look at guys in the interior. This is only for balls contained there. Okay, but what happens if 2 of them touch each other? Well, I just, so, and if 2 balls collide, touch, I stop, I freeze sigma for a moment, and then just combine them into a larger ball whose radius is the sum of those 2 balls. I put them into I replace them by, if 2 balls B1, B2 touch, I replace by B tilde, such that the union is contained in B tilde and the radius, say R1 plus R2 is equal to R tilde. And then what happens? Then the integral over B tilde of the energy, well, that'll surely be bigger than the integral over B1 plus the integral over B2 of the energy. And this is bigger than R1 plus R2 times this, which is equal to R tilde over sigma lambda epsilon of sigma. Okay, and so if two balls collide, I just replace them by a larger ball, and my lower energy bound. Well, that's true. Also, what happens with the degrees? So d tilde, the degree of the combined larger ball. Okay, there's this nice additivity property of the degree, and so this is going to equal d1 plus d2, and so then the absolute value is certainly bigger than the sum of the absolute values. And so R tilde over D tilde will be bigger than sigma, which is okay. If I have no cancellation, if I have equality here, then the ratio will still be sigma, but it can get, if there's cancellation, if the radii sum, if the numerator sums and the denominator loses something, then the ratio will get bigger. So for example, I can have a ball of degree +1 and degree -1 colliding. Then I replace them with a larger ball, that is degree 0. And so for that thing, R over degree is plus infinity. And that is no longer a minimizing ball. But anyway, but it still satisfies the estimate. Because, so I should say greater than this, because R tilde is at most, so yeah, so R tilde is at most sigma times D tilde. Okay, and so so we have this algorithm which says we start with this collection of small balls who have asserted without proof and not even correctly exist, and then we let them grow in this way. If they collide, we let them merge. If they hit the boundary, we stop worrying about them, and we can just keep on doing this indefinitely. At some point, they'll all hit the boundary and everything stops. But until then, I can just for any positive sigma, any sigma greater than this initial sigma, I can do this. And that's the proof of this proposition. And this is kind of nice. And so if I stop as in choice of sigma, I find a bunch of balls, and in each one the energy scales correctly, so to speak. So it scales like, roughly speaking, like the degree d times radius times log of radius over epsilon, which is what we want. That's what we expect to see. And the energy scales correctly. And there may be some complicated internal structure. There may be lots of pieces of this set S inside. We don't need to keep track of that. We just get the right bound on each one. Okay, any questions? And so this is what's called the vortex ball argument, or vortex covering, something like that. Let me say then quickly, so the ideas here. One, if the degree of psi around the ball is not equal to 0, then one. So remember, the degree is, well, it's the what is it? Well, so it's related to, it's the so psi has modulus greater than 1/2 on the boundary. And so the degree, so the definition of degree I claim implies that if size models we can have on the boundary, then the image of that ball contains a ball of radius a half. And so the vorticity is, well, anyway, so I claim that the integral over the ball okay, I don't have time to really convey why this is true, but that isn't hard. If the ball is bigger than epsilon, then the integral over the ball, let's say if of the energy is equal to the integral over the ball radius r. Well, okay, let's put it this way. It's the okay, and this is not 1, but this is like some constant pi over 4. Okay, and so this is then bigger than pi over 4 from above, and this is like the integral from epsilon out to r, and the integral over the boundary of the ball of radius s of the energy. And what happens is on every one of these radii, the ball, the energy is like a constant over epsilon. And this is related to arguments we gave in the proof of one of the lemmas from Monday. Okay, so if you have a ball of degree non-zero, then in this way we can say, well, if its radius is if it's small, then then our task is just to prove its energy is at least epsilon, and we can do it is at least order 1, which we can do in this way. If it's big, well, then we want the energy to be proportional to the radius over epsilon, and so from the first epsilon units of radii, we get a concentration order 1, and then for any additional radius, we get again a contribution is proportional to radius over epsilon. Okay, and so the lemma is not that hard to prove if the degree is non-zero for balls for the degree is non-zero. Then you have to mess around a bit if the balls, if they collide. I mean, so there's that. The headache is if the degree is 0, then it's really not quite true. And so we have to, in fact, treat differently the components of this set S with degree 0 and the components with degree non-zero. And if the degree is 0, then you have to sort of treat them. They're actually not, they may not be covered in this initial covering, and you have to do something different with them. And so this is the way in which I've lied in the statement of this lemma, and this gives rise to various technical headaches. But the basic idea is that start with this collection and grow them in this way, and then this function capital lambda we use for lower bounds on annuli by just integrating the naive calculus estimate, and this is what we get. And so then some technical adjustments or some technical messing around is necessary to deal with the issues I've been discussing about the ways in which the lemma earlier stated was not quite correct. So, okay, and so then on Monday, so we can see it's pretty easy to prove the theorem I started with, the theorem that says that that gives us this nice vorticity concentration if we have only rather crude information plus energy bands. That's an easy consequence of the proposition because we've, remember, our task was to cover the set where S is small, where psi is small. And we can do this with small balls, and we can control the radii and the degree. That's what we've done. So we'll do that. Then for studying vortex dynamics, there's another ingredient which I won't really have time to talk about. but these are, I'll describe these very briefly. And so these are estimates that say, once we have a result like this, so this tells us, roughly speaking, we know a lot about what the vorticity looks like. We know that it's very concentrated near points. It tells us where it is up to errors of order. It tells us it's concentrated at these points C sub I. When the errors are small, the errors of order epsilon of the alpha. So we're really located where the vortices are. Once we do that, we can have very precise energy lower bounds. And moreover, we can say that if those bounds nearly hold, then we have a lot of information about what the function has to look like. So I'll describe those results briefly, and then I'll talk about how we use those to study vortex dynamics. You know, I told you a few days ago I was planning to stop next Thursday, a week from today. I found the Field Institute, without asking me, scheduled me. They put me on the schedule for the following week, the week of December 13th, I think it is. No, 14th, December 14th. And I'm not going to do all of that, but I may go over on December 14th because otherwise I can't finish this topic. So apologies to everyone who feels, who's here against their will and feels obliged to listen as long as I continue talking. So anyway, that's the plan, and I'll stop for today. Okay, any questions? Let me share this in the meantime. But if you have any questions, please unmute yourself or put it in the chat, and we'll see what we can do. So. But anyway, this is a pretty nice argument. I mean, it starts with the ingredients are just sort of simple calculus estimates, but one can assemble them in kind of a nice way to, and also you get quite a lot of information from these things. Okay, so I'm trying to. Okay, let me see, my computer has stopped responding. Okay, here's the chat again. Okay, so here's the file. It's reluctant to upload the file. I'll try again in a second. Okay, let's try this. I don't know. Okay, so that worked. Maybe this will work too now. Okay, for some reason, this is not being uploaded. But in the meantime, I'll try again. Any questions?
I had a quick hi. I would have a quick question. So how important is it that I saw you a couple of times assuming that psi is actually C1, and while you would usually only know that psi is an H1 function as solution to Gauss-Bayevsky. And obviously you lose like the pointwise control of the function. So how important is this difference or this assumption you made? This is like just to move around some technical headaches, or?
Yeah, so in fact, all these things are still true if you assume H1, but they're easier to prove for C1. And so we want to do things like, I have this function psi. I'd like to, when I compute the degree I'm integrating the gradient around a boundary. And so for H1 function, the trace of the gradient doesn't exist, or something. I have to, what I don't know what it means. And then there's a sort of easy way around it. But so what we're integrating around the boundary is a product of the function itself and the gradient. And so what happens? The gradient is H minus 1. The function is in H1. Sorry, you first take traces. So the trace is in H1 half, the gradient of the trace is in H minus 1 half. The duality makes sense, but just to avoid that stuff, I assume. But yeah, so everything is still true if we assume only H1, but I wanted to bypass some technicalities. And you're right that for a gross PDFC, H1 is really the right setting.
Okay, thank you.
You're welcome. And somehow this my computer refuses to upload a file, so I'll post it someplace sometime. I don't know. Maybe I'll put it on my webpage, and I'll do that now before I forget. So okay. Anyway, I'm going to spend 2 minutes messing around and trying to get this on my webpage, and then when I'm done with that, I'll turn off this meeting. But
and then I have another question, a quick one.
Sure.
So assume that there's kind of no, everything is degree 0. Would this still, or would this still work? Could you still say that psi is like bounded away from the modulus of psi is bounded away from 0? No, you a priori you don't know that, or
yeah, they're still working. So what you might have in the degree 0 cases, I might have, for example, I might have a small dipole where there's a say a vortex degree plus and minus 1 very close to each other. And so when I even do this initial covering by balls, there'll be this cancellation, or there could be little places where the modulus drops down to 0, but nothing, but the winding number is 0 around. But you see, in the situations I want to apply this to, I'd like to start with this, for example, the solution of gross Petyatsky, and I put these vortices in the initial data. And so, and then I solve the equation, and I know they'll move around for a while. And so in these cases, there should always be some vorticity someplace, and it'll end up, and so the balls will have to be there. That'll be some balls to cover that. And so, but yeah, it's still true when the degree is 0. Let me see. It's just the conclusions are not so interesting. Okay, I don't have a very efficient way of putting this on my webpage, but we can do this. In the meantime, I'll try to upload again. Okay, let's see. Let's see, okay. So, okay, so it should be almost done. give it a try. Okay, so okay, yikes. Okay, December 3 lecture. There it is. Okay, good. And so then I find my webpage, find it there if you want. And okay, so if there are no more questions, I will sign off now. And see you guys on Monday, I hope. Okay, have a nice weekend.